Hi people, I hope we're doing well. As promised, some videos on 3.6, which we've broken up into two sections. First being the derivative of logarithmic functions, the second part being logarithmic differentiation. Let's tackle the first one first. Now, remember that this, along with the derivative of inverse trig, we needed to wait until after we introduced implicit differentiation, because even though a lot of these things we have formulas for, those formulas are derived by means of the process of implicit differentiation. Now, let's say that we're asked to find the derivative of the following: y is equal to natural log x. Well, if we do not yet know the formula for that, we do not know the differentiation rule for that, but we know the derivative of exponentials and we know implicit differentiation, then we can simply change the form. And we can change it, basically we can change the form from the logarithmic to its implied exponential equivalent, which is e to the y is equal to x. Now, if we know the derivative formula or rule for exponentials, we can certainly differentiate the left-hand side, e to the, because remember when we were dealing with chain rule stuff, it was e to the stuff. The derivative of e to the stuff is e to the stuff times the derivative of stuff. Well, if that stuff in this case is y and its implied relationship to x, then it's e to the y times y prime. On the right-hand side, simple linear, coefficient is 1, so its derivative is 1. Now, if we want to find y prime, which in this case is dy dx, we basically divide by e to the y. But remember, e to the y was equal to x. So we can substitute and we get y prime is equal to 1 over x. And this is how we basically have derived our rule for the derivative with respect to x of natural log x. And we know that it's 1 over x. And basically this is, and the fact that it's all nice and neat and tidy and stuff like that, this is one of the reasons why natural logs wind up being everywhere, everywhere in calc. Okay. So let's say we're asked to differentiate a logarithmic function that is a base other than e. So, log base 2 or common logs base 10 or log base whatever. It doesn't really matter. If it is a base other than e, then we have to make use of our change of base formula. But when we make use of that change of base formula, we need to remember that a right here is standing in for any numerical constant that defines the base of the logarithm. So if a is a constant, then natural log a is a constant, and we don't leave it like this, but we can pull 1 over natural log a out in front and treat it as a coefficient, because it is, right? If a stands in for any value, then let's say it's log base 2 of x. It's natural log x over natural log 2. Well, natural log 2 is a value, right? It is an actual value. You can plug it into your calculator and you can get a decimal approximation. And that's why we pull that out in front of natural log x as a coefficient. And if that's the case, then if we're asked to differentiate log base a, then we change it. And because it's a coefficient, it can be pulled out in front of the ddx, right? Because remember, derivatives are limits, and we were able to do that using the laws of limits. And therefore, when we differentiate natural log x, we get 1 over x, and then we basically multiply the two fractions together, and we get x natural log a. Now, I put the x out in front of the natural log a because oftentimes if we're not using parentheses or not real careful with our notation, there can be some ambiguity as to what is a part of the argument of the logarithm and what's not. But if x is out in front, and not, if you have something instead like, 1 over natural log a x, right, and you're not careful with your notation, this could be natural log a times x, or this could be natural log a x, right, and they could both be part. So I just always pulled the variable out in front of numerical logs like that, just because it basically cuts down on the ambiguity, and of course ambiguity leads to careless errors. But basically this is a danger, okay? Now, so we obviously now know the rules of natural log x and the derivative of natural log x and the derivative of log base a of x. And the only difference is this natural log a down here. Now, it should be no surprise that when it's natural log u, of course, u being a expression of x, that it would be 1 over u instead of 1 over x, 1 over whatever that expression is, and then we would multiply it by u prime. Well, multiplying it by u prime, you know, just in terms of expediency and efficiency, you can just sort of plop that into the numerator. So it winds up being u prime over u. And similarly, for log base a of some expression, some function u of x, it's u prime over u, but you got to deposit that natural log a in the denominator because of this right here, okay? Because basically the change of base. Okay, now, like I said, chain rule versions, not surprising. So let's go ahead and do some examples. Yay! Alrighty. This one right here, and of course we're going to jump right in with ones that, you know, fold into what we already know in terms of differentiation rules. This is going to be a product rule. So we have dy dx, and then let's do the first times the derivative of the second plus the derivative of the first times the second, and that's it. Okay. I mean, I guess you can write it without the brackets. I remember the brackets I use in order for when I go back to check my work. I want to the brackets indicate which factor of that term is my derivative, right? So this tells me that it's sine x, and 1 over x tells me I've taken the derivative of the other piece, okay? Now this one down here is similar, right? It's similar because it's a product. Now this one is a little bit different because this natural log right here requires the chain rule. But it's still a product rule problem, so we'll say the first times the derivative of the second. Now remember, the argument of the logarithm, boom, goes right down into the denominator. And then you just simply put the derivative of it in the numerator, plus the derivative of the first, derivative of x, times the second. And this, you know, not much simplification is necessary. Just go ahead and combine this x with the 2x that's already up there. And I'm going to get x squared plus 4. And this is my derivative. Alrighty. All right, let's go ahead and let's move on to some. Now, the great thing about logarithms and what they share, obviously, with trig expressions is there's always that possibility of changing the form using the rules that we have for those change of forms. When we're talking about logarithms, we refer to them as the property of logarithms. Now, this one right here, and that's supposed to be a v, so v times the natural log of 3v plus 1 to the 1/3, right? And when we start taking derivatives, we want to get rid of the radicals and turn them into fractional exponents. Well, that fractional exponent right there, by properties of logarithms, can be pulled down as 1/3 3v plus 1. And of course, that 1/3 can be pulled out in front, and I'm going to get v times the natural log of 3v plus 1. Now, that looks a whole lot tidier than that does right there. Now, when we're doing this, you need to remember that change of form is not the same thing as differentiation. A lot of students, when they get going really fast on a test, they'll sit there and they'll go, and they'll spend about 5 steps changing the form and then circle it and move on. They have changed the form, but they have yet to take the derivative. And it's just, you know, you look back and your brain is thinking, or sort of half thinking, because you're just basically, I have a lot down, I've arrived at a stopping point, and therefore I must have arrived at the stopping point, meaning the answer. And that's just not the case. So in this particular one, we need to remember that after we've changed the form, now we need to differentiate. And we have the first times the derivative of the second. And we plop the argument for the logarithm down into the denominator, put its derivative up in the numerator. The derivative of the first times the second, 3v plus 1, and there you go. And of course, this can wind up being simplified rather nicely. This v can go up there, and I'm going to go ahead and distribute the 1/3 because as I do, it's going to cancel with this 3 in the first one, and I'm going to get v over 3v plus 1. I just have to be careful that it doesn't cancel with anything in this second one, so I need to make sure that it sticks around. Okay, and there we go. Now that change of form was actually relatively minor. This one right here is going to be a little bit more egregious because what happens is I have one factor in the numerator, but I have two factors in the denominator if I'm going to pull it apart. And as I pull it apart, okay, and I'm going to take this 1/2 and I'm just going to leave it out here, all of the factors in the numerator leave us with positive logarithms. All the factors in the denominator leave us with negative. And now that I have that, this of course is a little bit easier to differentiate than that, because what you were going to have to do to differentiate that is put that whole argument in the denominator, and which is already going to make it a complex fraction. But its derivative, which was going to have to be done by the quotient rule, was going to go in the numerator. So you're just going to have a nasty complex fraction that needs to be resolved. If you actually use the properties of logarithms from the get-go, again, one of those moments where we stop, think, then do, right? What winds up happening is you wind up getting a much, much easier term by term or logarithm by logarithm derivative. Now remember that this one becomes 1 minus x. Now this was already a minus, but this is going to be a -1 in the numerator because the derivative of this is going to be this coefficient of x. So you could just let that negative cancel with this negative and put the 1 up there. This one, however, doesn't have a negative to cancel with the minus sign, and you basically are left with that. And if you want to distribute the 1/2, you can. If you don't want to distribute the 1/2, you don't have to. But this winds up being so much easier than torturing yourself with the complex fraction that is differentiating from this form. Okay, I mean, it could have even been worse because that 1/2 could have been, you know, the square root, because this is actually, if you back up one more step, this is actually what it is, because that 1/2 could pop up as a 1/2 power, which is of course this radical right here. Would you rather differentiate this or this? And I think the choice is, I think it's not even really a choice. Okay. Alrighty. Let's do this one. Y is equal to the natural log of the natural log of 1/x. Now, 1/x, we need to remember, is going to be the natural log of x minus 1, or the natural log of the negative natural log of x. And that's fine, okay? What we need to do from here is we simply need to differentiate. So we're going to take y prime. We're going to go ahead and put negative natural log x down here because that is the argument. And then, of course, we need the derivative of that, which is -1/x. Those negatives cancel out. I'm left with 1/x natural log x. Okay. Now, this one right here, okay, this one is one of those ones where you're going to want to pull it apart. There are three factors that are not capable of being combined, and therefore that's why they're still sort of sitting there independently. This is natural log of x, and we'll change the radical into a fractional exponent. Okay. And therefore we're going to have y is equal. Remember, every factor of the numerator gives us a positive logarithm, and every factor of the denominator gives us a negative logarithm. Now, from here, this is much easier to differentiate than that is. So let's go ahead, and y prime is 1 over x plus 1/2 times 3x minus 1 with a 3 in the numerator, right? So basically this is the coefficient that came along for the ride. This is u, and that's your u prime. And this winds up being 3 and 2x over x squared plus 1. And, you know, you can simplify it if you want. Becomes 1 over x plus, and you can pull the 3/2 out in front, or you can put the 2 down here. It doesn't really matter. Both are equally messy, I guess. So I probably pull the 3/2 out in front and do that, and then pull the 6 out in front and do that. Not quite sure why, but that just looks prettier to me. And there you go. Okay. Now we're going to have two more problems before we call this one quits and then move on to logarithmic differentiation. So let's do 2 problems that deal with logarithmic. They're composite, so they're chain rule, and they're basically the same functions, just one is f of g of x and the other is g of f of t. So alrighty, we're doing the inverse sine of the natural log of x. Well, remember, this is arc sine of stuff. So what is the derivative of arc sine of stuff? Well, remember that if we're dealing with arc sine of u, that's going to be u prime over the square root of 1 minus u squared. Now, could you actually do this the long way by calling this sine of y is equal to natural log x? Sure. And actually, you want to know what? We can probably do that here as soon as we're done doing it this way. But let's go ahead and do it by formula first of all, just recognizing the fact that our u in this particular case happens to be a logarithmic function. Now, so if we're going to follow this formula, we know that it's 1 over x times the square root of 1 minus natural log x squared. Or, 1 over x, 1 minus natural log x squared. So there's your derivative. Now, you need to remember and be very careful, because the natural log of x squared is 2 natural log x, because the argument is being raised to the second power. But the natural log of x squared is not the same thing. This is the whole function being squared, the whole expression. This is simply the x. So remember this, okay? That means that you cannot simplify this down here. Okay. Well, let's go ahead and do it. Let's do it the other way when we did the inverse trig by implicit. So we have y is equal to, and I just can't get myself to do the inverse sine right now. We'll call it arc sine. We'll call it sine y is equal to natural log x. Well, let's go ahead and differentiate. With respect to x, that becomes cosine y prime, and this is 1 over x. So y prime is equal to 1 over x secant y. Well, that means that it's 1 over x secant of arc sine. And you think natural log x is not a ratio. Well, sure it is if you put it over 1. And it winds up being just, it winds up seeming a little bit odd to actually, use that as a measurement of a triangle side. But, it's not that big of a deal. So if we're dealing with arc sine, we're dealing with natural log x, and we're dealing with 1. So just as if that were x, this becomes 1 minus natural log x squared. And if I'm looking for the secant of that, the secant is hypotenuse over adjacent. And of course, that winds up being exactly what I got when I did it by formula. But of course, like I've said time and time again, formulas can be forgotten, or they can be misremembered, whereas this basically, there's nothing too formulaic about any of this. There's no complex formulas, and basically doing it by implicit and then using your knowledge of trig to find the ratio that's required. Alrighty. This one. So we have the natural log of arc sine of t. Okay, so that basically means that, remember that when we're doing natural log of u, it's simply u prime over u. Of course, there's no simply about this, but so what we're going to do is we're going to go ahead and take, and I'm just going to change this into arc sine because it's annoying me. Basically, we're going to take the argument, shuttle it down to the denominator, and then of course it's going to be 1 minus t squared. So it actually winds up being arc sine of t times 1 minus t squared, and that right there winds up being your derivative. And it's not clean and it's not tidy, but it's not really all that complicated either. Like I've said before, like none of these problems are beyond your grasp because you understand, you have the knowledge to do all of them. The only thing that's going to be quote-unquote difficult about any of these is just how many things are being brought to bear. So in that sense, they're not difficult, they're burdensome and they're tedious at times, but we just kind of need to continue. It's time and exposure that basically is going to aid us in all of this. Now, we're going to, in the next video, tackle a few, we're going to explain again logarithmic differentiation, and then we're going to tackle a few more problems. As always, if you have any questions, please do shoot me an email. Bye.